Welcome to the High Voltage AI podcast. We are really thrilled to have you with us for another deep dive. Now, this deep dive is part of a special week-long series we're running in the High Voltage AI newsletter on Substack. Our mission this week really is to help educate electric utility engineers like you on overhead and underground construction types. We're exploring, why we use them and the unique characteristics of each. Okay, so today is Thursday, and we're zeroing in on a particularly exciting area within small modular reactors. We're talking advanced materials, controls, and construction systems. These aren't just small tweaks, right? This feels like a fundamental shift in how nuclear power is, designed, built, and operated. Let's unpack this a bit.
Yeah, it's really fascinating, actually. What we're seeing is how decades of pretty rigorous research and development in fields that seem separate, material science, AI, they're all converging now. And this synergy, it's what's directly enabling the commercial deployment of small modular reactors. It's solving challenges that, frankly, held back advanced reactor development for a long time.
That's a powerful idea, that convergence. Okay, let's start right at the foundation, though. The materials. Small modular reactor operation, it demands materials that are just, way beyond traditional nuclear specs. What kind of extremes are we actually talking about here? And I guess, why can't the old materials cut it?
That is a really important question. What are these extremes? Well, we need materials that keep their strength, their integrity, at operating temperatures hitting 950 degrees Celsius.
950, wow.
Yeah, compare that to maybe 320 degrees Celsius for a traditional pressurized water reactor, so much hotter. And beyond heat, there's immense neutron radiation. We're talking lifetime exposure, up to 10 to the power of 22 neutrons per square centimeter.
That sounds like a huge number.
It is. And the material can't get brittle under that bombardment. Plus, they need to stand up to really corrosive stuff, molten salts, high-temp steam, even helium coolants. And they have to do all this while cycling thermally, day in, day out. Traditional materials, they just degrade way too fast.
That really is extreme environment engineering. So, okay, what are some of these next-generation materials that can actually take that kind of stress? What makes them so different?
Right, so we're seeing a whole new class of materials coming through. Hastelloy N, for instance, that's the primary structural material for molten salt reactors. It's an alloy, nickel molybdenum chromium iron, engineered specifically to run continuously up to 704 Celsius. And it does that with minimal corrosion, like less than 25 micrometers a year in fluoride salts. And it handles radiation really well.
Okay.
Then for steam generator tubes, in environments over 700 degrees Celsius, there's Inconel 617. We also have things like Fincrol alloys, that's Ficroloy for accident-tolerant fuel cladding, better oxidation resistance, and oxide dispersion strengthened steels, ODS steels, for really extreme radiation environments. These aren't just stronger materials. They're engineered, at the atomic level to hold up where conventional steel just fails.
And making sure they're up to snuff must involve some serious testing.
Oh, absolutely. Rigorous processes, complete material certification, from the raw elements right through to the finished part. Accelerated aging tests, irradiation testing, and advanced non-destructive evaluation, like ultrasonic and radiographic testing, is key.
Okay, so beyond the structures, you mentioned fuel cladding. The fuel itself has seen a huge innovation, right? This tristructural isotropic fuel, TRISO. This sounds like more than just an improvement. It feels like a total rethink of nuclear fuel, enabling safety and these super high temperatures.
That's exactly right. TRISO fuel is not just a pellet. It's a multi-layer design. Think of it like a tiny, tiny pressure vessel. You start with this minuscule kernel, maybe 425 micrometers across, of uranium oxycarbide. Then you layer it. Porous pyrolytic carbon to handle fission gases. Then dense pyrolytic carbon. Then a really crucial layer, about 35 micrometers of silicon carbide. That acts as the pressure vessel and the fission product barrier. And finally, an outer protective coating of pyrolytic carbon. Each layer has a job, making the whole thing incredibly resilient.
So the nasty stuff stays inside the particle itself.
Precisely. Fission products are contained at the microscopic level. That fundamentally changes the safety case compared to traditional fuel rods.
And the performance numbers, I hear, they're pretty wild.
They really are, yeah. TRISO fuel lets you operate continuously up to 1,600 degrees Celsius.
1,600?
Yeah, drastically higher than traditional fuel limits.
Yeah.
And the burn-up capability, we're looking at 150,000 to 200,000 megawatt days per ton of uranium. Compared to about 60,000 for traditional fuel.
Yeah.
So much more energy out of the same amount of fuel. And crucially, it holds on to over 99.9% of fission products, even at that extreme 1,600 Celsius temperature.
That's impressive. Are companies actually making this stuff now?
Oh, yes. Kairos Power, for example, they've already made over 300,000 TRISO fuel particles just for testing their Hermes reactor. So, validated production. And X-Energy uses TRISO particles in graphite compacts for their XE100 design. That helps enable their planned 60-year plant life.
Okay, another material innovation, you mentioned molten salt coolants, especially for those molten salt reactors. What's the big advantage there over, say, water?
Right, molten salt coolants like FLIBE, that's a fluoride salt, 2.5 euros, they are revolutionary. They melt around 459 Celsius and operate continuously between 600 and maybe 700 degrees Celsius. The key advantages, well, first, low pressure operation. We're talking near atmospheric pressure.
Compared to the high pressure in current reactor.
Exactly. Traditional PWRs run at 155 bar.
Yeah.
So much lower pressure means less stress on components.
Yeah.
They offer incredibly high temperature capability. They're chemically stable. They don't break down under irradiation like water can. And they're inherently safer because their boiling point is super high, over 1400 Celsius. Meaning a loss of coolant exit, like the kind we worry about in traditional reactors where the water flashes to steam.
Yeah.
It's virtually impossible. The salt just won't boil off.
Okay, that makes sense. Is managing the salt tricky?
It requires care. Yeah. You need continuous purification, managing the chemistry, controlling redox potential to minimize corrosion. It's critical. And companies like Kairos Power, they use custom fluoride salt blends optimized specifically for their reactor designs.
All right, so we've got these incredible new materials, the backbone, really letting small modular reactors run hotter, longer, and inherently safer. But even the best body needs a sharp brain, which brings us to controls. This sounds like another massive shift moving away from the old analog systems.
Absolutely. And if you connect this to the bigger picture, traditional nuclear control systems, even in quote-unquote advanced plants, like the Westinghouse AP1000, they're fundamentally limited by those analog constraints. You have separate systems for different functions, limited processing speed for complex calculations, hardwired designs that are a nightmare to modify, and often relies on operators watching, maybe 18,000 different indicators in the control room.
18,000? Wow. Okay.
Yeah, it's a much more reactive approach rather than proactive.
So what does this shift to digital mean for small modular reactors? How does it actually, improve things? How does it change how you run the plant?
Well, small modular reactor digital control systems are integrated platforms. They can process in real time over 100,000 data points per second.
Huge difference.
Massive.
Yeah.
And that processing power lets you run sophisticated, advanced algorithms, things like model predictive control, optimization routines, significant AI integration. NuScale's system, for instance, uses what they call a highly integrated protection system, or HIPS. It's a digital architecture, redundant digital processors, fiber optic networks, and of course, heavily fortified with cybersecurity. It's not just about speed. It fundamentally changes the operational philosophy towards more autonomous, more anticipatory control.
And these aren't just faster systems. You're saying they're genuinely smarter. They can do things that were just, impossible before.
Precisely. They offer advanced functions like automatic control rod positioning, integrated control of the steam system, fully digital safety systems with diverse ways to actuate, and real-time efficiency optimization algorithms, constantly tweaking things for best performance.
And you mentioned model predictive control. What's that about?
Right, MPC, that's a really smart approach. Instead of just reacting to what's happening now, the system builds a mathematical model of the whole reactor. It uses that model to predict how the reactor will behave, say, 10 to 30 minutes into the future.
Okay, so it looks ahead.
Exactly. It anticipates changes. It can proactively adjust control rods or steam flow for optimal control and efficiency rather than just reacting after the fact.
Yeah.
Plus, there's significant AI integration. We're seeing machine learning for anomaly detection, spotting tiny issues early, predictive maintenance, figuring out when components might need attention before they fail, and even AI assisting operators during unusual conditions.
Now, all this digital tech, all this connectivity, it screams cybersecurity risk. Nuclear plants are critical infrastructure. How are they tackling that?
Yes, nuclear cybersecurity is absolute paramount.
Yeah.
You can't overstate it. It demands specialized solutions following strict regulations, NEI 1310, RG 5.71, IEC 62645, IE 1686 for smart devices. The core strategy is defense in depth. Layers of protection, physical security, obviously, but also rigorous network segmentation, keeping safety-critical systems totally separate.
Air gaps.
Air gaps, yes.
Yeah.
Multi-factor authentication, continuous monitoring for anything unusual. NuScale, for instance, they implement those air gap networks, use strong encryption for all digital communications, employ intrusion detection systems, and have automated responses ready if a cybersecurity event is detected. It has to be comprehensive.
Okay, let's shift gears from the sort of micro-level details of materials and controls to the macro, actually building these things. Additive manufacturing, 3D printing.
Yeah.
That sounds like a real game changer for making nuclear parts, right? Pushing boundaries.
It really is. It allows for incredibly complex shapes, integrated cooling channels, things that are just impossible or prohibitively expensive with traditional machining. And it does this while drastically cutting down manufacturing time and material waste. We're talking processes like laser powder bed fusion for stainless steel, Inconel 625 parts, electron beam melting for titanium, high-temp alloys. But crucially, these have to meet those strict nuclear quality standards. ASME Boiler Pressure Vessel Code Section 3 and QA-Ed 1. Every printed part has to be just as robust, just as qualified.
So what are the tangible benefits? What are companies seeing?
Well, design flexibility is huge. Like I said, internal cooling channels, you can design them optimally with 3D printing, maybe get a 40% improvement in heat transfer.
40%?
Yeah. And material use, you might use 95% or more of your raw material. Traditional machining can sometimes waste half of it as shavings.
That's a big cost saving.
Huge. X-Energy, they've used 3D printing for things like heat exchanger plates, control rod guides, pressure vessel internals for their XE100. And they reported, I think, a 70% reduction in manufacturing time for some complex parts.
Wow. And quality control. How do you ensure a 3D printed part is flawless?
It's built into the process. You have in-situ monitoring, layer-by-layer inspection as it's being printed, and then rigorous post-build, non-destructive testing ultrasonic, radiographic inspections, just like traditional parts. It's a totally different way of thinking about manufacturing quality.
Okay, so that's individual components, but the whole construction idea for small modular reactors is different too, right? Modular construction, transportation, this isn't like building a giant plant on site over years.
No, not at all. This is a major differentiator for small modular reactors. They are designed to be factory-built modules.
Like building blocks.
Essentially, yes. Highly engineered building blocks. This means manufacturing happens in a controlled factory environment. Precision assembly. And that gives significant advantages. You accelerate the schedule because you can do factory work and site preparation at the same time.
Parallel processing.
Exactly. It also cuts costs because factories get better and faster with repetition of the learning curve and you use standard processes. Plus, no weather delays like you get on a traditional construction site.
Okay, it sounds great on paper, but these modules, they must be massive. How on earth do you move a reactor module? Sounds like a monster trucking job.
It is a huge logistical undertaking, no question. It requires specialized systems. NuScale, for example, their reactor modules weigh up to 700 tons each, fully assembled in the factory.
700 tons.
Yep. Then they prepare them for transport. It could be rail, barge, or specialized heavy-haul trucks, potentially over thousands of miles. This involves things like self-propelled modular transporters, SBMTs. These things can handle 44 to 60 tons per axle. Incredible machines. And hydraulic gantries or strand jack systems, maybe up to 800 tons capacity, for lifting and placing them precisely at the site.
The route planning must be intense.
Meticulous. Bridge load analysis, checking every single clearance along the way.
Yeah.
Often needs temporary road closures, special escorts. It's a major operation.
Okay, so the giant Lego block arrives. What happens then? How does the final site integration and assembly work? Putting these massive pieces together accurately must be tricky.
It involves sophisticated techniques, definitely geared for precision and speed. The site itself is prepared beforehand. Maybe seismic isolation systems are installed, prefabricated modular foundations ready to go for rapid installation. Then you bring in the heavy lift cranes, we're talking over 1,000-ton capacity sometimes, hydraulic systems, laser alignment tools to ensure everything lines up perfectly.
Is anyone actually doing this now?
Yes. TerraPower's Natrium construction out at the SMR project in Wyoming started in June 2024. That's a prime example. They're projecting, I believe, a 24-month construction timeline. Compare that to 60 months, 5 years or more for traditional nuclear plants.
Big difference.
Huge. And the workforce needed is smaller too. Peak of maybe 1,500 workers versus over 5,000 for a big traditional build. This modular approach really changes the economics and the deployment speed.
Okay, this is all sounding incredible piece by piece. The materials, the controls, the construction, each seems like a breakthrough. But the real magic, I suppose, is how they all work together. So what does it mean when you truly integrate these things into one system?
Yeah, that's the key point. Connecting it all back. Small modular reactor success hinges on seamless integration. It's not just about having the parts. It's about how they function as a whole.
So like
smart materials with embedded sensors feeding data back to the control system in real time about their condition. Adaptive control systems that can actually adjust how the reactor runs based on changes in material properties as they age or degrade. AI systems predicting material issues or maintenance needs before they become problems. It also means things like fully testing the integrated control systems in the factory before shipping the module.
Ah, so it arrives almost ready to plug and play.
Closer to that, yes.
Yeah.
Plug-and-play control modules, maybe even remote commissioning capabilities once it's on site. It dramatically streamlines getting the plant online. The synergy is where the real power lies.
Can you give us a concrete example? Where has this kind of systems integration really been demonstrated?
Absolutely. Kairos Power's Hermes reactor demonstration back in 2023 was a real landmark. It validated the integration of that TRISO fuel with advanced digital monitoring. It showed real-time molten salt chemistry management using predictive algorithms of the system, anticipating and adjusting the salt conditions. And it used factory-built modules with those integrated control systems.
So all the pieces working together.
Exactly.
Yeah.
That level of integration allowed them to use AI for optimizing both material performance and control parameters simultaneously. It showed capabilities just impossible with older tech, proving the synergy works in the real world.
Okay, but with all this cutting-edge stuff, ensuring it's reliable, it's safe, it performs exactly as designed, that must require massive testing and validation, right? You can't just assume it'll work.
Oh, absolutely. Rigorous testing programs are critical. There's safety for performance and, frankly, for getting regulatory approval. Materials go through intense irradiation testing. Facilities like the Advanced Test Reactor, the high-flux isotope reactor, they can simulate 60 years of reactor life exposure in just 2 or 3 years.
Wow, compressing time.
Yeah. TRISO fuel goes through dedicated programs, too, like the Advanced Gas Reactor Fuel Qualification Program, full burn-up tests, high-temperature accident simulations, really pushing it to the limit.
Then the control systems.
Thorough verification and validation, following IE standards, extensive cybersecurity testing, real-time performance validation under all sorts of scenarios. And finally, yes, complete system testing in the factory before the module even ships. The Nuclear Regulatory Commission reviews and approves these factory acceptance testing programs. It ensures everything works together correctly before it even leaves the factory door.
All this amazing technology coming together. It's not just changing reactors. It must be creating whole new avenues for engineers, for professionals. Let's talk about the careers opening up because of these advancements. This is where it gets really interesting for a lot of you listening.
Indeed. We're definitely seeing high demand in specific areas. Nuclear materials engineers, obviously, focusing on advanced alloy development, TRISO fuel R&D, molten salts compatibility issues. Additive manufacturing engineers are also becoming crucial. That nuclear additive manufacturing market is projected to be over $2 billion by 2030. So expertise in 3D printing processes, quality control for critical nuclear parts. Very valuable.
Makes sense. What about the control side?
Roles for nuclear control systems engineers. People who can work with these complex digital systems, design them, implement AI and machine learning algorithms within them, and linked to that, nuclear cybersecurity engineers. Hugely important. That market's expanding too, maybe over $500 million just in nuclear cybersecurity. Often needs certifications like CISSP or GCIH.
And the actual building and moving.
Yes. On the construction side, definitely a strong need for nuclear construction managers who understand modular builds and specialized transportation engineers. People who get heavy haul logistics, handling nuclear components safely. It's a unique skill set.
So let's try and wrap our heads around this. What's the big takeaway here? The small modular reactor technology we've talked about today. It really feels like this convergence point. Decades of research in materials, controls, construction, all coming together now into systems you can actually deploy commercially.
That's exactly it. This integration, it enables small modular reactors to have capabilities that genuinely exceed traditional nuclear performance in many ways.
Yeah.
And at the same time, it solves those big manufacturing and deployment challenges, the time, the costs that historically limited nuclear expansion. It's really a technological foundation that seems ready now for widespread deployment. It's turning all that cutting-edge research into actual hardware, actual operating systems, poised to change the energy landscape.
So this deep dive, we've explored these advanced materials like TRISO fuel and molten salts, those sophisticated digital controls using AI, and the game-changing modular construction, all making small modular reactors a commercial reality. Now, thinking about all this, what advanced technology experience do you have, maybe from your own field, that could transfer over to small modular reactor applications? Perhaps you've seen similar leaps in materials or digital systems or modular approaches in other industries. Are you seeing opportunities like these opening up at your company? Share your experiences with us. We'd love to hear how these innovations connect with the work you're doing. Okay, looking ahead. Tomorrow, we'll conclude this week-long series. We'll focus on a comprehensive career action plan. We'll examine specific certifications, training programs, industry networks, things that can help enable a successful transition into these exciting small modular reactor engineering roles. And just to quickly recap the week, Monday was the small modular reactor engineering revolution and careers. Tuesday, we dug into passive safety and factor manufacturing. Yesterday, Wednesday, was all about grid integration and industrial heat applications. Today, of course, advanced materials, controls, and construction innovation. And tomorrow, Friday, we wrap it up with that career action plan skills, certs, and networking. As always, if you'd like to leave feedback or have any questions, please feel free to reach out to our producer, Julia Squire, on LinkedIn.